15 gemstones that will vanish forever. Last chance to see them. A few gemstones on this planet are reaching their final moments. Not rare, ending. Crystals born from volcanoes that no longer exist. Colors the earth cannot recreate. Mines sealed by ice, silence, or time itself. 15 stones, each with a story closing forever. From blues formed under vanished glaciers, to reds forged in heat the modern earth no longer produces, to greens created by geological accidents so precise they happened once, and never again. This is your last chance to see them. 15 gemstones on the edge of extinction. Beauty the world is about to lose. Don't forget to press and hold that like button, leave a comment, and hit subscribe before we begin. Ranked 15th, blue Hemimorphite, a calm blue born from unsettled earth. A blue as calm as shallow water, born in a land that rarely knows stillness. The blue Hemimorphite of the Democratic Republic of Congo carries a paradox in every fragment. Serenity laid over a landscape shaped by upheaval. What looks like a soft mineral veil, thin, translucent, cooling, emerges from a region where nothing remains untouched by conflict or uncertainty. From the first moment it appeared in the mineral record, this gemstone stood at the intersection of beauty and instability. Hemimorphite is common across the world's zinc deposits, but the Congo variant, those glimmering pools of ocean-colored silica, formed under an unrepeatable balance of chemistry and chance. Inside the abandoned zinc veins of Katanga, slow oxygenation transformed metal into color. Groundwater threaded through fractures just long enough to dissolve and redeposit silica. Trace elements settled into perfect equilibrium. Disturb the water flow, alter the oxidation gradient, shift the microchemistry by a fraction, and the blue vanishes, replaced with a pale, indifferent white. This fragility defined the material long before conflict did, but the conflict sealed its fate. The region where blue Hemimorphite was discovered lies within one of Earth's richest mineral corridors, a place where copper and cobalt dominate every economic calculation. When global demand rose, informal miners moved into old workings, followed by militias seeking control of whatever profits could be extracted. Entire zones changed hands without warning. Routes that were open one week were barricaded the next. In that chaos, the shallow zinc pockets, never economically significant, became inaccessible, forgotten, or deliberately sealed. The finest specimens came from cavities the size of a cupped hand, discovered during brief intervals of relative safety in the early 2000s. They were not part of a large vein or continuous seam. Each one was an isolated breath of color trapped inside broken rock. When tunnels collapsed or water flooded the passages, those pockets were entombed. No record exists of any consistent production. No shipment in the last decade has offered material approaching the luminosity of earlier finds. Markets reacted the only way they could when supply disappears suddenly, first with disbelief, then with silence. Collectors noticed that the deep blue plates and botryoidal clusters simply stopped entering circulation. Museums cataloged their older pieces and found no new comparables. Dealers, once confident they could obtain more with time, gradually acknowledged that the mines were no longer reachable and may never be again. The color that defined Congo's Hemimorphite has not reappeared in any region, in any geological environment, or in any exploratory attempt. The earth did not run out of the stone. People ran out of the ability to reach it. Its extinction is not geological, it is territorial. A gemstone erased not by erosion or pressure, but by the narrowing of corridors, the closing of tunnels, and the shifting map of fragile authority. Blue Hemimorphite, light as breath, delicate as glaze, became impossible to find precisely because the ground beneath it would not stay still. A calm blue born from unsettled earth, now slipping permanently beyond reach. Ranked 14th, pink Danburite, Mexico. In the volcanic spine of central Mexico, there once existed a color so quiet that nearly everyone overlooked it. Pink Danburite, now spoken of with a reverence it never enjoyed while abundant, began its life in anonymity. Its earliest crystals were dismissed as curiosities, minor deviations from the clear Danburite that miners treated as little more than sparkling waste. What they were truly holding was a mineral chapter the earth wrote only once. The revelation emerged not from rarity, but from misunderstanding. For decades, gemologists believed Danburite was a colorless story, pure, transparent, dependable. But archived field notes from San Luis Potosí tell of miners who occasionally encountered faint rose infusions, subtle enough to be mistaken for impurities or surface staining. Museums mislabeled the first specimens. Academic papers ignored them. An entire shade existed in the world, quietly waiting for someone to recognize what it truly was. It was only in the late 20th century that mineralogists realized the truth. The pink hue was not an accident, not contamination, but the result of a transient hydrothermal sequence that has not occurred again. A narrow pulse of manganese-rich fluid had infiltrated a cooling volcanic fracture for just a brief geological moment. When that vein shifted, the color stopped. Pink Danburite, contrary to early belief, was never common, only overlooked. By the time the scientific world understood what it had missed, the mountain had already closed its doors. The mine responsible for the finest material collapsed in stages, its tunnels narrowed by rockfall, its chambers drowned by slow seepage. Geological surveys from the early 2000s found nothing but sealed pockets, unreachable caverns, and a silence that marked the end of a process nature had no intention of rehearsing. Pink Danburite is not vanishing because demand has grown. It is vanishing because the earth no longer makes it. The precise conditions that shaped its lattice existed for a blink and disappeared before anyone realized their significance. Every surviving crystal is a remnant of a moment that cannot return, a fragment of time captured before the story was understood. As collectors finally grasped what had slipped through their hands, the market changed abruptly. Stones once sold cheaply now appear only in old inventories, mislabeled boxes, or private holdings that rarely see daylight. What remains is finite, fragile, and already caught between history and extinction. It raises a quiet question. How many other minerals were lost before anyone learned their names? Pink Danburite did not fade. It was simply recognized too late. A revelation postponed until its subject had already passed beyond reach. Ranked 13th, Afghan Lapis Lazuli, the blue that outlives civilizations. There are stones valued for rarity, others for brilliance. And then there is Lapis Lazuli from Badakhshan, a blue that served not merely as a gem, but as a thread binding civilizations together for more than 6 millennia. Among all vanishing minerals, few carry a legacy as deep, as layered, and as quietly burdensome as the Afghan lapis. High in the Hindu Kush, where the mountains splinter into impossible ridges, the Sari Sang mine has remained active longer than any known mineral source on Earth. Historians can trace its workings back to the Bronze Age, when miners armed with stone tools pried fragments of ultramarine sky from the bedrock. Some of those early pieces traveled thousands of kilometers, becoming beads in Mesopotamia, amulets in Egypt, and sacred pigment in the temples of Persia. Before the world agreed on borders, it agreed on this blue. No gemstone has carried more meaning across more cultures. Egyptians crushed it into powder to paint the eyelids of pharaohs. Medieval monks ground it to illuminate manuscripts, each stroke costing a small fortune. Rulers wore it, priests guarded it, and artists revered it. Even now, traces of Afghan lapis hide inside the irises of Renaissance saints, frozen in pigment that remains unchanged after 500 years. But the weight of legacy is also the weight of expectation, and expectations strain what remains. Sari Sang has always been difficult to reach. The path that winds toward the mine clings to cliffs, shifting each season. Every generation built upon the void left by the one before, extracting layers that do not regenerate. As modern conflict tightened its grip on Badakhshan, routes closed, armed factions claimed control. Access became unpredictable. What had survived for 6,000 years now faces an erosion not of geology, but of continuity. The finest lapis, the deep ultramarine saturated with golden pyrite, came from narrow seams that are nearly exhausted. The material still extracted today is thinner, paler, often marbled by calcite. Craftsmen who worked with the stone for decades report that blocks with the old intensity have become as rare as relics. Even pigment makers, long accustomed to scarcity, Acknowledge that Afghan ultramarine of classical quality has almost disappeared. The world's most enduring blue may outlast every empire that touched it, yet it may not outlast the generation now living. Modern collectors chase pieces not for their rarity alone, but for their lineage. A fragment from the same seam used in ancient Mesopotamian seals carries a resonance no laboratory-created color can imitate. But if access to Sari Sang continues to shrink, the physical link to humanity's oldest artistic traditions may close with it. This gemstone has chronicled civilizations. Its fate now may chronicle their fragility. Lapis lazuli is not simply a mineral nearing disappearance. It is a story nearing its final chapter, one written in blue long before history learned to write it all. Ranked 12th. Volodarsk Heliodor, born in a chamber of ancient fire. Long before the first city was built, before writing, before even the earliest traces of agriculture, a chamber of molten granite cooled beneath what is now northern Ukraine. In that chamber, hidden kilometers below a forest that did not yet exist, nature began a slow and deliberate act of crystallization. Volodarsk Heliodor was not discovered until the 20th century, yet its story began hundreds of millions of years earlier, inside a geological environment so precise that it reads like an instruction the Earth followed only once. Heliodor, the golden member of the Beryl family, is usually the child of pegmatites, giant mineral pockets where heat lingers long enough for atoms to arrange themselves with uncommon clarity. But Volodarsk was different. It formed inside a numidilytic chamber, a rare transitional zone where vapor, magma, and superheated gases interacted with extraordinary discipline. Here, fluorine-rich fluids infiltrated fractures, stripping elements from the surrounding rock and depositing them again in shimmering order. Iron in its trivalent state infused itself into the growing beryl lattice, giving rise to a yellow so deep it bordered on amber. Pressure declined at the exact rate needed for hexagonal prisms to stretch uninterrupted. Temperature cooled slowly enough for transparency to build layer by layer. The result was a kind of crystalline architecture that seemed intentional. Long, flawless columns with termination faces so sharp they looked cut rather than grown. The chamber did not merely create crystals, it created monoliths. Some heliodors reached lengths of 2 meters, each one a complete record of the chamber's final exhalation. When miners opened the pockets in the mid-1900s, they found crystals standing like golden spires inside a cathedral of quartz. Mineralogists who examined them realized they were seeing not a typical pegmatite, but the fossilized remains of a vanished fluid system, one that no longer exists under modern Ukraine. But the genesis that made Volodarsk possible was also its undoing. When the ancient chamber finally cooled, the pathways that once carried mineral-rich gases collapsed. The delicate balance of vapor pressure that created the golden hue vanished. The system became a closed relic, effectively ending the possibility of new growth. By the time geologists mapped the structure, its life cycle was long completed. The second collapse came from the surface. Political shifts, environmental restrictions, and the eventual sealing of the quarry ended all access to the pocket-bearing zones. Today, the tunnels are flooded, the walls fractured, and the crystal chambers unreachable. Nothing in the region recreates the temperatures, pressures, or chemistry that shaped the original Heliodor. Volodarsk Heliodor is not just rare, it is geologically finished. Its birthplace is gone, its engines have stopped. Every surviving crystal is a chapter from a story the Earth no longer tells. A golden shard from a chamber that cooled into silence millions of years ago, never to open again. Ranked 11th. Charoite, the violet anomaly the Earth shouldn't have made. Across the Siberian plain, where the Lena River carves through volcanic remnants older than most continents, lies a lavender swirl that should not exist. Charoite, discovered only in the 20th century but forged under conditions the Earth rarely recreates, has always stood apart from the minerals surrounding it. Its appearance defies simplicity, silky bands of violet folding into pearlescent ribbons, each layer twisting as though shaped by motion instead of pressure. To hold it is to witness an anomaly, one that geologists still struggle to classify without resorting to metaphors. The stone formed deep within the Maroon Massif, a region where carbonatite intrusions collided with limestone, metamorphosing the rock through a combination of heat, fluids, and chemistry that seems more alchemical than geological. The reaction zone was narrow, the window for creation brief. Most metamorphic minerals follow predictable paths, but charoite emerged from a triple intersection of potassium feldspar, limestone, and rare earth-bearing fluids, an intersection so unlikely that no other known deposit has successfully reproduced it. Thin fibers align themselves into a pattern that behaves like light caught in motion. Under illumination, the surface shimmers as if layered with brushstrokes. No other silicate produces this texture naturally at this scale. Even its optical behavior, a form of directional pearlescence, sits at the boundary of what minerals are expected to do. For decades, early samples were misidentified as dyed stone or composite material. Miners who first encountered it believed it was man-made. Petrographic studies revealed a paradox. Charoite's structure is stable, yet it looks fluid. Crystalline, yet it behaves visually like fabric. The more scientists examined it, the clearer the conclusion became. The mineral did not merely form, it transformed, reorganizing its internal fibers, as if responding to a set of pressures that no longer exist in the modern Earth. The anomaly extends beyond appearance. The Murrin deposit is a geological island, an isolated alkaline complex with no twin elsewhere on the planet. Without this exact combination of calcium-rich limestone, intrusive carbonatite, and rare earth-laden hydrothermal fluids, charoite does not appear. Attempts to predict its formation zones have failed. Exploratory drilling outside the massif found nothing. As far as the geological record shows, the Earth created charoite once, in one locality, with no second draft. Today, access to the deposit is limited not by conflict, but by the sheer harshness of Siberia. Winters close the region for months. The ground freezes into permafrost. Supply routes vanish beneath snowstorms. And even when mining resumes, the remaining pockets are small. The richest chambers, those bearing the swirling lilac patterns, have largely been extracted. What is left is thinner, patchier, often overprinted with other minerals. Collectors return to earlier specimens because the newer material cannot replicate the sensation of motion trapped inside stone. Charoite is not disappearing because it is rare. It is disappearing because the set of conditions that formed it was a singular irregularity, a geological whisper that the planet has not spoken again, a stone that looks fluid inside a world of solids, an anomaly, fading toward extinction. Ranked 10th, neon sphene, where light obeys the geometry of stone. Among the minerals that bend light into color, few perform with the mathematical discipline of neon sphene. Titanite, the mineral's formal name, has long been known to mineralogists for its high dispersion, but the neon variant from the mountains of Pakistan and the volcanic provinces of Madagascar elevates that property into something bordering on the engineered. Its fire does not shimmer. It fractures into spectral lines so sharp they feel calculated, as if the crystal were built for precision rather than beauty. The mineral's geometry is immediately recognizable. Titanite grows as wedge-shaped crystals, triangular forms defined by asymmetric planes that intersect at exact repeating angles. This is not randomness frozen into stone. It is order. Every face aligns with a consistent lattice. Calcium, titanium, silicon, and oxygen locking into a configuration that leaves no guesswork in its symmetry. When light enters the crystal, it is compelled, almost forced, into splitting. The dispersion value surpasses that of diamond, yet the phenomenon feels more analytical, as if the mineral is executing an equation millions of years old. The neon variety intensifies this behavior. Trace elements, often vanadium or chromium, shift the absorption profile, allowing green and yellow wavelengths to transmit while red and violet fracture into luminous edges. Under sunlight, these edges sharpen into thin, blade-like flashes. Under artificial light, the crystal behaves differently, dispersing into rapid pulses of color that seem to flicker faster than the eye can comfortably follow. Collectors describe it not as sparkle, but as light in coherent motion. The environments that produce this precision are equally exacting. In Pakistan, the neon titanite emerged in alpine clefts where tectonic plates forced granitic bodies against marble, creating micro-pockets of unusual chemistry. The conditions had to remain stable long enough for crystals to elongate without interruption. Even minor shifts in temperature would stunt their growth, and impurities would cloud the lattice. In Madagascar, the crystals formed in pegmatites enriched with rare trace metals, pockets where cooling occurred slowly enough for dispersion to develop its full potential. Such precision is fragile. A few degrees too much heat, and the lattice loses transparency. A slight change in trace element ratio, and the neon glow dims. An interruption in cooling, and the crystal terminates before reaching gem quality. These environments no longer behave the way they did when the finest crystals formed. In Pakistan, exhausted clefts now yield only small, clouded fragments. In Madagascar, once productive pegmatites have been mined to their cores, leaving behind little more than broken feldspar and quartz. The neon variant in particular appears to have depended on a sequence of conditions so narrow that the Earth no longer recreates it. Its fire is not merely brightness, it is geometry transformed into physics, angles distilled into color, an optical precision that seems closer to human design than geological chance. Neon sphene does not fade quietly. It disappears the moment the Earth deviates from perfection. A mineral defined by precision, now undone by the slightest imprecision in the world that once shaped it. Ranked ninth, Poudretteite, the gem that lived only long enough to be desired. Some gemstones inspire admiration, a few inspire devotion, but Poudretteite, one of the rarest minerals the Earth has ever allowed, triggered something deeper, a quiet, persistent obsession among collectors who understood how close this gem came to disappearing before it was even recognized. Its story begins not with abundance, but with a single fragment. In the late 1960s, a pale, translucent crystal was found in the Poudretteite family quarry on Mont Saint-Hilaire in Quebec. It was small, unremarkable, and nearly dismissed as a byproduct of the area's complex alkaline geology. For decades, it sat in mineral drawers, labeled and forgotten. Only later did researchers notice its unusual potassium-boron silicate structure, a lattice so delicate that growing large crystals seemed almost impossible. The mineral was named Poudretteite, but no one imagined it could exist as a gemstone. The moment gem-quality material surfaced, decades later and continents away, collectors began to chase a stone most of them had never seen. Reports emerged from Myanmar's Mogok region, a handful of pink, nearly transparent crystals with a softness in color that resembled evening light filtered through silk. The stones were small, fragile, and unlike anything from Quebec, and they were almost immediately gone. Unlike other rare gems, Poudretteite offered no promise of a mine, no hints of a larger deposit, no geological pathway that could lead to predictability. Every specimen seemed to surface by accident, retrieved from pockets so limited that miners did not return to them. Most crystals shattered during extraction. Others were lost before anyone recognized their significance. This unpredictability fueled the obsession. Dealers whispered about fragments the size of a grain of rice selling for more than diamonds. Museums began searching old collections for misidentified pieces. Collectors traveled to gem shows with magnifiers in hand, hoping for a glimpse, just a glimpse, of the pink shade that had grown into legend. Poudretteite is so scarce that many seasoned gemologists have never held one. Some have never seen one outside of photographs. Fewer than a dozen faceted stones above 1 carat are known to exist. The largest, weighing just over 3 carats, is treated as an artifact, not merchandise. No market graph can track it because no market exists. Supply is not low. Supply is effectively zero. Attempts to locate new deposits have failed. The original quarry in Canada yields nothing large enough for cutting. The pockets in Myanmar that produce the finest material have vanished beneath landslides, closed tunnels, or the simple erosion of time. The stone appears only where geology intersected with luck, and that intersection has ceased. Obsession leaves behind a particular kind of silence. The silence collectors hear when they realize the chase is over, not because they reach the goal, but because the goal no longer exists. Poudretteite stands at the edge of extinction, not with volume, but with absence. A gemstone that lived long enough to be desired, just not long enough to be found again. Ranked 8th, Maw Sit Sit. the green that demanded a price from everyone who sought it. At the northern edge of Myanmar, where the Kachin highlands fracture into cliffs laced with serpentine and jadit, a shade of green emerged that belonged to no established mineral family. Maw Sit Sit, named after a remote village in the Jade Tract, appeared not as a single crystal, but as a metamorphic mosaic, a compressed tapestry of cosmochlore, jadeite, chromium jade, and dark amphiboles fused together under conditions so violent that the borders between them blurred. The result was a green unlike any other, neon, electric, a chromatic pulse running through stone. But this beauty carried a price. Maw Sit Sit does not form in calm, geological environments. It forms where the earth grinds against itself. The same tectonic forces that birthed it also entombed it within some of the most treacherous terrain in Southeast Asia. The pockets containing Maw Sit Sit occur in serpentinized zones that twist unpredictably through mountains riddled with sinkholes and collapsing slopes. Landslides carve paths without warning. Rivers change courses overnight. Access to the deposit requires hours of trekking through monsoon-cut ridges, where entire sections of ground can shift beneath a single footstep. Every piece extracted from this environment is a fragment of a place that has always resisted human presence. For generations, miners in the Jade Tract have risked more than fatigue. Sudden flooding of tunnels, rockfalls triggered by distant tremors, and the absence of medical support in an isolated region where minutes can decide survival. Maw Sit Sit, with its vivid green streaks, often lies adjacent to jadeite seams, zones already claimed, contested, or controlled. Extraction becomes negotiation, movement becomes caution, and every stone carries the weight of human hazard. Unlike standalone gemstones, Maw Sit Sit is a record of pressure so immense that minerals with conflicting chemistries were forced together. Its formation demanded the breakdown of older rocks, the infusion of chromium-rich fluids, and the compression of fragments into a unified mass. Nothing about its existence came without strain, and the same is true of the people who touch it. In recent years, the situation has intensified. Political instability in northern Myanmar closed many of the routes leading to the deposits. Permissions shifted, borders hardened, and regions once accessible became restricted. As mining halted, the world discovered that most high-grade Maw Sit Sit had come from a handful of narrow zones. Zones now unreachable. The brightest neon material, once carved into inlays and ceremonial pieces, has not appeared in new supply for more than a decade. Heritage loss spike, a color slipping into memory. For local artisans, Maw Sit Sit is more than a stone. It is part of a cultural landscape woven through jade markets, rituals, and craftsmanship. Its disappearance marks not just the closure of a deposit, but the dimming of a regional identity forged from greenstone. Maw Sit Sit does not vanish quietly. Each piece represents a negotiation with geology, danger, and time. A green born from strain and lost when the world can no longer bear its cost. Ranked 7th, Benitoite, the blue that disappeared the moment its mine closed. In the foothills of the Diablo Range in California, a narrow seam of altered serpentinite once held a blue so vivid it rivaled the color of deep oceans. Benitoite, California's state gem, was discovered in the early 1900s, a mineral that seemed almost accidental in its beauty. Its triangular crystals reflected light in a way no other natural stone did. Sapphire blue in daylight, an ethereal icy glow under ultraviolet light. For decades it appeared to be nothing more than a geological curiosity, rare but not irreplaceable. Only when the mine closed did the consequences begin to unfold. The gemstone formed under conditions so peculiar they border on the improbable. High-pressure fluids carrying barium and titanium infiltrated fractures in a serpentine body, reacting with silica in the host rock. The process required precise temperature decline, a narrow chemical balance, and a transition zone between metamorphic environments. When these conditions aligned, benitoite crystallized in star-like formations, sharp, perfect, and unmistakably singular. The deposit at the Dallas Gem Mine was not a vast field. It was a cluster of pockets stretching across steep, unstable slopes. Each pocket was finite, each cavity a closed chapter. When mining became increasingly difficult, when landslides grew frequent, when costs rose and safety declined, the operation could not continue. The tunnels were sealed, the claims retired, and the earth reclaimed the ridge. Once the mine shut down, the world realized the magnitude of what had been lost. Benitoite is not merely rare, it is region-locked, formed in a sliver of geology that has no equivalent anywhere else on the planet. Without that ridge, without those fractures, those fluids, that temperature gradient, the mineral cannot be born again. The consequence echoed through markets, museums, and scientific archives. Collectors who once took the stone for granted began revisiting their holdings. Museums resisted long-standing pressure to deaccession their pieces. Newcomers entered the field only to discover that no amount of money could conjure new supply. In a world saturated with synthetic gems and replicable colors, Benitoite stood alone, a blue that cannot be grown, predicted, or replaced. The scientific community felt the loss as well. Benitoite's perfect trigonal symmetry, its unusually high dispersion for a blue gem, and its UV fluorescence made it a reference point in mineralogical studies. With the mine closed, researchers found themselves working with what little material remained in old collections, samples already touched, cataloged, and exhausted by decades of analysis. As time passed, the absence became the story, and the story became the measure of its worth. Benitoite is now a gemstone defined by consequence, the consequence of a geological moment that has ended, a ridge that no longer yields its stars, and a world that discovered the value of a blue only after the earth stopped making it. A color preserved in fragments, its future limited to the hands that already hold it. Ranked 6th, Burmese Painite. The perfect crystal the earth chose not to make twice. In the central reaches of Myanmar's Mogok Valley, a region already renowned for gems born from improbable pressures, there emerged a mineral so structurally exact that for decades it was believed to be unique. Painite, named after the mineralogist who first identified it, stood as an outlier not because of color or brilliance, but because of how precisely the earth had arranged its atoms. It was as if the planet attempted a design far too intricate to replicate, succeeded briefly, and then abandoned the effort entirely. Painite belongs to a crystal system governed by symmetry, angular consistency, and elemental precision. But its chemistry is notoriously complex. A borat lattice incorporating zirconium, aluminum, oxygen, and trace amounts of vanadium and chromium, an arrangement so delicate that even a minor deviation collapses the possibility of crystal growth. Most borate minerals form readily, painite forms reluctantly, requiring a narrow intersection of fluids, heat, and host rock composition that reads more like an experiment than a natural process. The atomic spacing within painite aligns at distances that neither ruby nor Sphene, the valley's more famous children, can mimic. Its trigonal structure demands that zirconium settle into positions that are rarely stable in metamorphic conditions. Even the slightest fluctuation in temperature or pH disrupts the build, leaving only microscopic shards. The few crystals that did survive bear termination faces so sharply defined they appear carved, not grown. For decades, only 2 such crystals were known. 2 on a planet filled with minerals. When additional specimens surfaced in the early 2000s, the world expected a larger deposit. But the new material revealed a truth more exacting. The crystals occurred in scattered micro-pockets, each pocket representing a moment in geological time when conditions aligned with improbable precision. None were large, none repeated, none indicated a seam or vein. Painite did not form continuously. It appeared momentarily, like a single clear tone struck in a chaotic landscape. Attempts to model its formation exposed the limits of current mineralogical understanding. Simulations showed that the zirconium to boron ratio needed to be exact. The oxidation state of vanadium had to fall within a narrow window. Pressure gradients during metamorphism had to transition smoothly rather than abruptly. It was not merely rare, it was conditional to the point of impossibility. As mining in Mogok shifted, as tunnels flooded or closed, the remaining pockets became unreachable. And with them went the last chance to observe painite forming in nature. Modern material is sourced only from leftover fragments, secondary sorting, or old tailings. No new crystal pockets have been found in more than a decade. Painite's disappearance is not the loss of a deposit. It is the loss of a mechanism, a geological choreography the Earth no longer performs. The mineral endures in photographs, museum drawers, and a few guarded collections. But the conditions that shaped it, down to atomic precision, have dissolved into the deep past. What remains are fragments of a design nature attempted only briefly, then chose not to revisit. Painite is the consequence of perfect alignment, and the inevitability that perfection cannot be sustained. Ranked fifth, Tanzanite, a blue the Earth will never make twice. At the base of Mount Kilimanjaro, where the shadows of ancient volcanic flows cut into the foothills of northern Tanzania, a single strip of Earth gave rise to a blue the world had never seen before. Tanzanite, found only in a sliver of land barely 8 kilometers long, owes its existence to a collision of geological circumstances so local, so site-specific, that its disappearance would mean the extinction of its entire kind. The gem began as a form of zoisite, a mineral common across metamorphic terrains. But beneath Kilimanjaro, the chemistry shifted. Vanadium infiltrated the crystal lattice, altering how it absorbed and released light. Pressure folded the rock into angled corridors, creating zones where heat rose and fell in careful gradients. When the final metamorphic pulse passed through the region, the lattice locked into a trichroism unlike anything on record. Blue from one direction, violet from another, burgundy in low light. Nowhere else on Earth did this combination occur, and nowhere else has it occurred since. For decades, the world treated Tanzanite as a gift from a landscape still forming. But gifts from young mountains have consequences, especially when the gift forms only once. The mining zone is narrow, fractured, and deeply pocketed. Its gemstones confined to vertical chimneys that plunge unpredictably into the ground. As miners chased the color downward, tunnels grew steeper, hotter, and more unstable. Sections collapsed. Water seeped in. Ventilation became dangerous. Extracting Tanzanite turned into a negotiation with the mountain itself. When a gem has only one birthplace, every shift in that landscape echoes through the global market. As the richest pockets emptied, prices climbed. Large stones became scarce, then rare, then practically historical. Families who once found crystals near the surface now dig through layers of collapsing schist for fragments. Younger miners speak of chambers their fathers described, chambers that no longer exist. Governments intervened, hoping to regulate extraction, protect miners, and preserve what little remained. But no policy can change the geology. The deposit does not regenerate, and the conditions that formed it are long gone. What remains today is the lower portion of a system already in decline. The deeper the tunnels go, the thinner the veins become. Meanwhile, the world's appetite for Tanzanite accelerated. Jewelry houses promoted it as a once-in-a-lifetime gemstone. Collectors bought up older pieces, and speculative markets formed around the idea that the supply might vanish within decades. The gem's fate became intertwined with global desire, an imbalance that only hastened the pressure on the region. Singularity of origin spike, a gem tied to one map point on Earth. If the mines close, Tanzanite does not shift production elsewhere. It simply stops existing. A blue shaped by one mountain, in one valley, under one geological event, faces an endpoint written into its birth. Tanzanite's beauty is undeniable, but its fragility lies in the fact that the world will never make it again. Ranked fourth, Burmese Ruby, the crimson legacy that outlived empires. There are gemstones whose value lies in scarcity, others in brilliance. But the ruby of Mogok belongs to a different order. Its legacy is older than the borders surrounding it, older than the kingdoms that once fought to possess it, older even than the languages first used to describe its glow. Mogok ruby is not merely a mineral. It is one of humanity's longest, unbroken lines of fascination. An ember passed from civilization to civilization across nearly 1,000 years. High in the Shan Plateau of Myanmar, the Valley of Mogok has been mined since at least the pagan kingdom of the 11th century. Chronicles from this era speak of stones red as the heart of a pigeon, carried as tribute to kings who believed the gems held the essence of life itself. In the centuries that followed, traders from Persia, Yunnan, and Bengal traveled to the valley in caravans, crossing mountain passes to reach a source so revered that entire trade routes were shaped around its reputation. The hue that made Mogok legendary, its saturated crimson, its faint fluorescence under daylight, became the gold standard by which all other rubies were measured. The greatest courts of Asia guarded them in royal treasuries. The Mughal emperors carved them with sacred verses. European monarchs sought them for coronation jewels. Every era inherited the belief that Mogok ruby was not merely beautiful, but sovereign, a mineral granted a status once reserved for relics. The stone's formation mirrored its destiny. Deep beneath the valley, marble layers rich in aluminum and chromium underwent metamorphism under temperatures and pressures so specific that even slight variations erased the possibility of ruby. Mogok is one of the few places on Earth where these conditions align with consistent accuracy. The ruby does not merely come from Mogok. Its very identity is entwined with the valley's geology. Nowhere else does marble breathe out red with this depth. For more than 8 centuries, generation after generation dug into the same hillsides. Entire families traced their lineage through the mines, fathers teaching sons, mothers sorting gravel washed with river water, children learning the sound of marble cracking under the weight of tools older than themselves. The ruby became part of the cultural landscape, woven into rituals, poetry, courtship, myth. Today, that continuity stands at its edge. Mogok's most famous pockets have thinned. Tunnels that once produced pigeon blood stones now yield mere trace hints of color. Marble is fractured, exhausted by centuries of extraction. Political restrictions further limit access, turning what was once a living legacy into a quiet archive of memories. The ruby that shaped dynasties is now disappearing not only from the earth, but from the culture that sustained it. Young miners leave the valley, traditional lapidary workshops close. The gem that outlasted empires may not outlast the generation born today. Mogok ruby is not simply a stone nearing extinction. It is a legacy nearing silence, a lineage of color, faith, and history held together by a valley the earth no longer replenishes. Ranked third, Larimar. The Caribbean blue the earth was never designed to make. In the southern mountains of the Dominican Republic, where extinct volcanic vents rise like the spines of a sleeping creature, the earth concealed a contradiction. Larimar, an azure pectolite found nowhere else on the planet, appears with the calm of shallow Caribbean water, yet it was born in the throat of ancient fire. Its blue is so striking, so improbable, that geologists once questioned whether the mineral had been altered by human hands. The truth was stranger. Larimar is a geological anomaly, the rare moment when nature contradicts its own rules. Pectolite, by every standard of chemistry, forms in dull whites and muted grays. It is a mineral of quiet tones, its fibers pale and unassuming. Yet in one extinct vent within the Baharuco Range, copper and calcium interacted under conditions so narrow, so impossibly specific, that the mineral took on blue, then deepened into turquoise, then hardened into a pattern resembling the sky reflected on a restless sea. No model predicted this. No known environment duplicated it. The earth produced Larimar only in this place, and seemingly by accident. The fibers of Larimar are arranged in a way that scatters light unevenly, creating clouds, waves, and concentric ripples. The stone behaves less like crystal and more like trapped water. That pattern is not natural to pectolite. It is not natural to volcanic stone. It is not natural to the conditions that formed it. Everything about the gem is the result of a structural deviation that should have collapsed back into ordinary white mineralization, but didn't. It stabilized, impossibly, into blue. Local legends sensed its strangeness long before science did. Villagers believed the stone had fallen from the sky or risen from the sea, a fragment of the horizon captured underground. Early explorers searched for its source in riverbeds, thinking it washed in from elsewhere. Because how could such a color come from the interior of a volcano? Even when specimens were collected in the early 20th century, they were misidentified, misplaced, forgotten. Larimar hid for decades behind the assumption that pectolite could never be blue. When its true origin was rediscovered in 1974, the anomaly finally revealed itself. The deposits formed within narrow lava tubes, ancient channels that once carried molten rock toward the coast. As seawater infiltrated through fractures, mineral-rich fluids cooled inside pockets the size of clenched fists. A shift in copper concentration here, a cooling glitch there, and the improbable conditions aligned long enough to turn white stone blue. The vents cooled. The chemistry vanished. The anomaly ended. Today, miners descend 300 to 400 meters into unstable shafts to chase the last veins. The volcanic tubes are fracturing. Groundwater floods the lower levels. The mountain grows more dangerous each year. Geologists confirm that most of the original pockets are exhausted. What remains is thinner, paler, lacking the vivid patterns that define the earliest material. Larimar is not disappearing because it is rare. It is disappearing because its existence was never meant to be repeatable. A blue born from fire, shaped by water, trapped inside stone. A contradiction the earth produced once, then quietly closed the door on. Ranked second, red beryl. A color the earth could barely afford to create. In Utah's Wah Wah Mountains, where desert winds carve silence into the volcanic ridges, a gem the color of concentrated sunlight flickers in seams so narrow they could be mistaken for cracks. Red beryl, often called the rarest of all gem-quality beryls, was not formed through abundance or stability, but through a sequence of geological risks so improbable that each crystal stands as the product of sacrifice, the earth giving up equilibrium for a moment long enough to create red. Most gemstones emerge from conditions that nature can reproduce. Red beryl does not. Its formation requires all the variables that normally destroy minerals. Heat high enough to destabilize beryl, volcanic gases rich in manganese, fractures that must stay open yet not collapse, cooling rates so narrow that a few degrees difference erases the color entirely. It grows not in generous pockets but in thin veins within rhyolite, where superheated gas pulses carry the exact ratio of elements needed to paint beryl red. Too much manganese, and the structure distorts. Too little, and it fades to pale pink. Any quiver of temperature, any interruption in pressure, and the lattice fails. Hundreds of thousands of mineral attempts ended as nothing. Only a handful completed the transformation. Sacrifice spike. The price of becoming red. Red is the rarest color in the beryl family because the chromium and manganese needed to create it compete with the lattice itself. The crystal must give up stability in order to take on color. It grows slowly, micrometers over years, its hexagonal channels stretching at the edge of collapse. Many crystals break internally as they grow, leaving only shards. The survivors are few, often too small to cut, and found in crevices barely wide enough for a fingertip. The miners who seek them pay a similar price. In the Wah Wah Desert, the heat bends the horizon. The rock is brittle, fractured by old volcanic vents. Access involves steep climbs, loose footing, and hours of labor for the chance of finding a fragment no larger than a grain of rice. Even commercial operations produced astonishingly little. Entire seasons yielded only a handful of cuttable stones. Those who worked the claims spoke of days chipping through rock for nothing, then moments of disbelief when a glint of crimson appeared. Tiny, perfect, impossibly rare. As demand grew, the desert revealed the limits of its generosity. Most accessible veins were exhausted. Deeper seams thinned until they vanished. The remaining pockets proved too dangerous or too unstable to pursue. Fragility of existence spike. A mineral too rare for its own survival. Red beryl is not running out. It was never present in quantities large enough to run out. Its rarity is its identity. Born from conditions that bordered on destruction, surviving only in crystals that balanced on the edge of failure. Every stone is a record of a moment when the earth risked collapse to create color. Every faceted gem is the final product of sacrifice measured atom by atom. Red beryl does not vanish because of loss. It vanishes because the world cannot afford the cost of making it again. In first place, Kashmir Sapphire, a vanished blue held only by memory and snow. Silence is where the story of the Kashmir Sapphire begins, and where it ends. High in the Zanskar range of the Himalayas, above clouds that drift like pale ghosts across the ridges, a small glacial valley once held a blue so soft, so velvety, it seemed woven from the sky at dusk. For a few short decades in the late 19th century, miners uncovered crystals that glowed as if lit from within, their color carrying a calm that felt older than language. The world named it cornflower blue, but the term fails. The stone was not the color of flowers or water or air. It was the color of quiet. The mines at Patter existed only as long as the mountain allowed them to. Snowstorms erased paths overnight. Avalanches sealed entrances. Entire seasons passed where no sound crossed the valley except wind. When work resumed, miners dug through layers of marble split by ancient pressure, their hands tracing veins so thin it seemed impossible that something of such softness could come from stone. Then, almost as suddenly as it appeared, the sapphire vanished. The primary deposit was exhausted by the 1930s. The tunnels collapsed, the fractures closed, and the mountain reclaimed the land with a stillness so complete that even geologists struggled to identify the old workings beneath the snow. No new pocket has ever been found. The valley is now silent, the marble untouched, as if the earth closed a book it never intended to reopen. Most gemstones go extinct because of conflict, or consumption, or the end of a deposit. Kashmir Sapphire disappears because the moment that created it simply passed. Its formation required a blend of heat and pressure during the Himalayan uplift, a delicate metamorphic window when aluminum-rich fluids moved through marble at a precise temperature band. This window closed millions of years ago. The mountain cooled, the chemistry shifted, the process ended. What remains is the emptiness left behind when nature finishes a masterpiece and moves on. Collectors speak of Kashmir Sapphire with reverence, not because it is rare, but because it cannot return. Its absence defines its value more than its presence ever did. Museums preserve the finest pieces behind glass, allowing only soft light to touch them. Auction houses treat each appearance as a cultural event. Jewelers no longer carve it, they protect it. Today, the valley that birthed the stone lies quiet under snow. No machinery hums, no tunnels open, no footsteps mark the slope. A visitor standing there would see only empty ridges, a white horizon, and an absence so complete it becomes its own kind of presence. The blue is gone, but the memory of it lingers in the stillness. Kashmir Sapphire is the rarest not because so little remains, but because the world knows with certainty that nothing more will ever come. Some gemstones vanish when their mines close. This one vanished when the earth stopped dreaming of blue. If a color can vanish from the earth forever, what does it mean to truly preserve beauty? The stones you've just seen are not vanishing because we use them, but because the moments that created them have already passed. Volcanoes cooled, mountains closed, chemistry shifted, and the conditions that once aligned with impossible precision will not return in our lifetime, or any lifetime. What remains now are fragments of endings, a blue preserved only in silence, a red forged on the edge of collapse, a green carved from danger, and colors the earth has already decided not to make again. If these stones disappear, their stories remain, as reminders that even the most enduring beauty can be temporary. Which of the 15 gemstones felt the most irreplaceable to you? Your answer may be different from mine, and that is how legacy survives, not in the stone, but in the memory of those who cared enough to look.